EEE EC 201 Electrical Circuits 1. In this lecture, we will study another energy storage element, the inductor. In the previous lectures, we have studied about two passive elements, the resistor and the capacitor. The resistor is an element that dissipates energy delivered to it in the form of heat, whereas a capacitor stores the energy delivered to it in the form of an electric field. The inductor is a passive element. It is very much similar to the capacitor, except that it stores the energy delivered to it in the form of a magnetic field. Under steady state condition, the capacitor can be replaced by an open circuit equivalent. In case of an inductor, under steady state condition, the inductor can be replaced by a short circuit equivalent. Now, before we study about the inductors, it is very important for us to understand the basics of magnetic field and magnetic flux lines or permanent magnet. Now, a magnetic field basically exists in the region surrounding a permanent magnet, which can be represented by flux lines. Similar to electric flux lines, magnetic flux lines, however, do not have origins or terminating points. They just exist in loops. The magnetic flux lines radiate from the North Pole and move towards the South Pole and then returns to the North Pole through the metallic bar. Note that the spacing between the lines inside the bar are equal, and outside the bar the lines are symmetric. That is, if 3 lines goes in this direction, the other 3 lines will go in this direction. The magnetic flux lines are represented by the symbol Chi. The strength of a magnetic field in a particular region is directly related to the density of flux lines in that region. For example, if we consider the figure over here, the strength of the magnetic field at point A is twice than that of point B. This is because the number of field lines or flux lines at point A is twice than that at point B. At point B, there are 3 lines, whereas at point A, there are 6 lines. Hence, the strength of the magnetic field at point A is twice than that of point B. If a non-magnetic material such as glass is placed in the flux path surrounding a permanent magnet, an almost unnoticeable change occurs in the flux distribution. However, if a magnetic material such as soft iron is placed in the flux path, the flux lines pass through the soft iron rather than surrounding air, because flux lines pass with greater ease through magnetic material than through air. Magnetic field. A magnetic field represented by concentric magnetic flux lines is present around every wire that carries an electric current. That is, any electric wire that carries a current will have magnetic flux lines around it in a circular form. The direction of the magnetic flux lines can be found simply by placing the thumb of the right hand in the direction of the conventional current and noting the direction of the fingers indicating the direction of the magnetic flux lines. This method is commonly called the right hand rule. If the conductor is wound in a single turn coil as shown over here, the resulting flux flows in a common direction through the center of the coil as shown over here. A coil of more than one turn produces a magnetic field that exists in a continuous path through and around the coil. SI units. Magnetic flux is measured in Webers, WB. Symbol is the capital Greek letter phi, which is this one. The number of flux lines per unit area is called the flux density and is denoted by the capital letter B and is measured in Tesla, T. In equation form, B equals pi by A. The flux density of an electromagnet is directly related to the number of turns of and current through the coil. The product of the two, called the magnetomotive force, is measured in ampere turns, AT, as defined by F is equal to Ni, ampere turns. Permeability. Another factor that affects the magnetic field strength is the type of core used. Materials in which magnetic flux lines can readily be set up are said to be magnetic and to have a high permeability. Again, note the similarity with the word permit used to describe permittivity for the dielectrics of capacitors. Similarly, the permeability of a material is a measure of the ease with which magnetic flux lines can be established in the material. That is, permeability basically tells us how easily magnetic flux lines will be established in the material. Just as there is a specific value for the permittivity of air, there is specific number associated with the permeability of air, which is mu naught equals 4 pi into 10 to the power minus 7 Weber per ampere meter. The ratio of the permeability of a material to that of free space is called its relative permeability. That is, mu r equals mu divided by mu naught. Induced voltage. Faraday's law of electromagnetic induction. If we move a conductor through a magnetic field so that it cuts magnetic lines of flux as shown over here, a voltage is induced across the conductor that can be measured with a sensitive voltmeter. That is all it takes. And in fact, the faster you move the conductor through the magnetic flux, the greater the induced voltage. Now, if we move a step further and move a coil of N turns through a magnetic field as shown over here, a voltage will be induced across the coil as determined by Faraday's law, which is E equals N d phi by dt. Here, N represents the number of turns in the coil and d phi by dt represents the rate of change of magnetic flux. Induced voltage. The inductance of a coil is a measure of the change in flux linking the coil due to a change in current through the coil. That is, L equals N d phi by di. The equation reveals that the greater the number of turns, which is N, or the greater the change in the flux linking the coil due to a particular change in current, the greater the level of inductance. In fact, we can derive the equation of voltage across an inductor using the following form. E equals N d phi by dt, which is equals to N d phi by dIL times dIL by dt. By substitution, we can obtain EL is equal to L dIL by dt. Voltage across an inductor. The voltage across an inductor can also be expressed using this formula, that is VL equals L dIL by dt. The equation clearly states that the larger the inductance and/or the more rapid the change in current through a coil, the larger will be the induced voltage across the coil. Inductance. So, what is inductance? When a current flows through a coil of wire with or without a core, it establishes a magnetic field through and surrounding the unit. This component of rather simple construction is called an inductor. Its inductance level determines the strength of the magnetic field around the coil due to an applied current. The higher the inductance level, the greater the strength of the magnetic field. In total, therefore, Inductors are designed to set up a strong magnetic field linking the unit, whereas capacitors are designed to set up strong electric field between the plates. Inductance is measured in henries, H. However, just as the farad in capacitors is too large a unit for most applications, most inductors are of the millihenry, mH or microhenry range. For inductors, 1 Henry is the inductance level that will establish a voltage of 1 volt across the coil due to a change in current of 1 ampere per second through the coil. If we compare these two equations over here, it can be determined that the inductance of an inductor with a ferromagnetic core is mu R times the inductance obtained with an air core. Example 1. For the air core coil as shown over here, A. Find the inductance and B. Find the inductance if a metallic core with relative permeability of 2000 is inserted in the coil. D equals 1 by 4 inch and length equals 1 inch. At first we have to convert the units to SI units. So D will be equal to 6.35 millimeter. A, which is area of cross section, we have to determine, which will be 31.7 micrometer square. L is 25.4 millimeter and L, which is inductance, equals 4 pi into 10 to the power minus 7 mu R n square A divided by L. From there we can determine L as 15.68 microhenry. The next question is, find the inductance if a metallic core with relative permeability of 2000 is inserted in the coil. Initially the core was air, now they are inserting a metallic core with relative permittivity of 2000. Hence, we know that L will be equal to mu R L naught. L naught is 15.68 microhenry and hence the new L will be 31.36 millihenry.